the solution, okay, at the front.
Oh, let me see, we lost. When I try record, I think that we lost speaker. Maybe we can ask to join. Hopefully that Rayleigh can join back. Oh.
Mute. So you can hear me now, right?
Yeah, yeah.
Okay, I'm sorry about the interruption here. Okay, so briefly, front tracking method is to use a geometric data structure, which we call the interface, to separate the computational domain, and then you solve partial differential equations separately, okay, on the two sides of the interface, and join the solution, okay, at the interface. The idea was first proposed, okay, by Richmeyer in 1950s. And in the 1960s, Moretti used that, okay, for aerodynamic simulation. And it was 1980s, Oliver Bryan, Mac Bryan, and James Glynn. And they proposed to the Department of Energy and to develop this method into all dimensions, 2 dimensions and 3 dimensions, to compute or simulate fluid interface problem. The idea is just like this. You have an interface and you have fluid solver on both sides. The most challenging problem in front tracking, I started working on this method in 1989 when I was a postdoc at the Quran Institute. The greatest challenge of the front tracking method is not the PDE solver, it's just a piece of cake. And it is not, the joined solution. It is, however, the resolution of the fluid interface, particularly if you have bifurcations of the interface. So over the last, since I joined as a postdoc in the group in Quran Institute, I had worked on this front tracking method for many years, and this is the group of the front tracking. This is James Glynn, and that was at the Science CSC. This was, I think, 2 years ago. In Valencia, Spain. And this is people who worked at in this group and on the front tracking method. Is Xingfeng here? I don't see it here. And however, these are the people who worked in the front tracking method, including my wife. And the idea of the major part of the front tracking method is that we have an interface data structure. And I'm not going to give details of the data structure, which is quite complicated and evolved for many years. And also when I try to do parachute method, I have to change a lot of this interface method. We have curves, surfaces, node, bound, triangles, and so on. What I would like to just demonstrate to you, some of the benchmark problems that we used to show the capability of the front tracking method. First, front tracking method can give very good subgrade resolution, and we made it quite robust for mesh deformation, and also bifurcation, in particular, three-dimensional bifurcation. And one of the benchmark problem that we sometimes compare with the level set method is that front tracking method as a Lagrangian method, and can maintain the geometry in high quality. And if you use level set method after just a few rotation, this slot, especially when this slot is very narrow, will be eroded very quickly. And so that makes front tracking method suitable for fluid structure interaction as well. This is mesh merging. And we applied this, since 2000. We have tried to make the front tracking method as user-friendly as possible. So we joined the DOE project and make the front tracking code somehow modularized. There are still problems in this code, like parallelization, node balancing, and the topological bifurcation is not perfect, but it's getting much better. And you can, this is just a very simple demonstration about the front tracking method applied to the so-called Rayleigh-Taylor instability. You have two fluid, heavy fluid and light fluid. And I show this because it gives you an idea how the interface evolves and how it is coupled with the fluid interface. Well, we do it forward and backward. So this, of course, when backward, it's not physical. And in particular, we applied, I think Xingfeng also joined this project, the study of the Rayleigh-Taylor instability. This is two-dimensional Rayleigh-Taylor instability. This is Rayleigh-Taylor instability for incompressible fluid, and this is a 3D bubble. And this one is what we want to study and compare with the experiment by the British atomic weapon establishment. That's David Young's, and he said experiment to measure the mixing rate. So we had a very good agreement with David Young's result. It was published in Physics Fluid and several other journals. And later, we also applied this to the diesel jet simulation. And it was in this presentation at Science CSE. And I met the Army Research Office program manager, Joe Myers, and he came to me. He said, "Xiaolin, your simulation is very beautiful. Can you think about something that benefit Army Research Office?" And it was just cracked my mind, and I responded that how about the parachute simulation? I didn't even realize how much challenge on there for the parachute simulation. And he said that's a good idea, so he gave me a seed grant and to just getting started. So this is the main topic that I'm going to discuss in today's talk: the front tracking application to parachute inflation. I should put parachute inflation here. And the main idea is try to use the front tracking existing data and the function structures to model the complex parachute dynamics. The parachute dynamics has three regimes: deployment, inflation, and the terminal descent. Many papers have been published on the study of the terminal descent. Now, terminal descent is relatively easy phase or region of simulation, because okay, the canopy of the parachute is already opened, and the change okay, of the interface is relatively small. Okay, now deployment is mostly okay, rigid body or simulation. Okay, and it is inflation okay, regime or inflation okay, process that we are mostly interested okay, because inflation is a very important phase okay, even though it is okay, quite short period of time, but it is very important because when you just plug your okay, string and you hope that the parachute will inflate, okay, and if it doesn't inflate, okay, you are in big trouble, okay, and therefore, okay, what we are interested is that we want to use the front tracking method to do the inflation from the folded state until okay, it is fully open. And I just give this a quote by Sean Fortwing of the University of Missouri, and he mentioned about how complicated okay, the parachute simulation is. And indeed, it is a very challenging problem. And so what I'm going to do is that I just give you the story, okay, how we solve the problem okay, one by one. And finally, okay, we pieces together okay, software okay, that can give the simulation of the parachute inflation realistically, physically, and scientifically, not just like a Hollywood okay, movie there. Okay, and so that is the objective. And I would like to mention about several people, okay, some people who have worked on the parachute simulation for many years. And, we referenced their papers, and we try to learn from their method. Okay, but okay, our method is quite unique, and we are very different from them. The model we used to study okay, the fabric parachute, okay, we call it the interface, but it's actually the open surface, okay, is by modeling or okay, mimic the parachute canopy, okay, using what we call the spring mass model. So what is a spring mass? I mean, this is a general structure of our code, okay, and so we have a fabric model. So fabric model is a very important part. And we have the fluid dynamics solver, which okay, we developed for many years. So this is a very mature part okay, of the software. And we have the spring mass model. Okay, we need to have the porosity modeling, and we also need to have collision handling. Okay, and so we will try to describe okay, each of these modules okay, as much as we can given the time slot okay, of this colloquium. Spring mass model. Okay, it's just okay. Assume that. Let me see if I have a picture of that. I don't have the picture of this. I think the picture is in a later time. Let's see. Yeah, this is like a spring mass model. So each okay element okay of the surface is considered being made by spring mass point and joint okay by the bond as a okay spring. And so this is the Lagrangian system, okay, and this Lagrangian system. There are several, okay, we can write the Lagrangian equation of that. And after that, okay, it is a system of ordinary differential equations, second order. But we can also make it the first order by introducing okay, velocity okay, of that. So it is become a big first order ODE a system. And this ODE system, okay, the first question, in fact, it was one of my colleagues asked me, is the following. Okay, what is the eigenfrequency? I mean, the system is a conservative system, okay, if we don't introduce damping force there. The first question asked by my colleague, Roman Samyalak, is what is the highest frequency? And he said the frequency, okay, of the oscillation is, okay, infinitely high, or there is no upper bound. So the first thing we did, and by one of my students, okay, was to prove that this system, no matter how many mass points you have, okay, there is an upper bound, okay, of the eigenfrequency. And we used to prove this by using two theorems. And I'm not going to give you details of that. The detailed proof of this is published in the communication of communication in computational physics, okay, CICP. And the idea is the following: the whole thing is a diagonally dominant system, okay, and therefore, okay, the eigenvalues, okay, are all real, okay, and therefore, when you take a square root of that and also take a minus, it is imaginary. So the whole system is conservative, and it is pure oscillatory, okay, conservative system if you don't, okay, introduce external force. And the second thing we proved is that there is upper bound, okay, for the eigenfrequency, and this, okay, angular eigenfrequency is bounded by this square root of 2m k m. K is the spring constant, m is the mass point mass. M, okay, is the number of labors, okay, or the maximum number of labors a spring point or mass point can have, okay. And generally speaking, the average is about 6, okay. And you know, you may have triangles with bad aspect ratio, so you can have m as high, okay, as 11 or 12. But on average, okay, the number of labors is 6. So that gives you the upper bound of that. And this was proven by the Gersh-Goring disk theorem or Gersh-Goring circle theorem. So this is just ordinary linear algebra, okay, and we teach every day, okay, to the graduate student, okay, and the details takes a couple of pages, okay, but the idea is there, okay. So you just get this one. So this gives you the upper bound of the eigenfrequency. Now, this upper bound eigenfrequency allows you, okay, to solve the ODE system, okay, explicitly. Okay, if the frequency is too high, okay, the eigenfrequency is very much like the velocity in the CFL condition in solving partial differential equation. We proved that there is upper bound, but in fact, numerically, okay, we showed it that the upper bound is a little bit lower. However, okay, theoretically, I just couldn't find any way, okay, to go from here to here. But numerically, okay, we did observed, okay, the bound, okay, and this is the oscillation, okay, you have from the spring mass system, and you know, these vertical lines are all, okay, square root of mk over m here. Okay, so the proof at least give you, okay, the upper bound, but this upper bound doesn't match with the numerical upper bound. Numerical upper bound is, okay, 1/2, okay, of the theoretical or analytical upper bound we proved. So there is a gap here, and I don't know how to prove close that gap. Okay, but I think that is good enough, because at least we know that the upper bound can be, there is an upper bound. So when you design numerical scheme, okay, for delta t, and you can observe that, okay, so that the system is stable. Okay, so this is just a simple model, okay, and how the spring mass system, you start from any, initial condition, gives a small perturbation, and in slashes. Okay, and we also carried out convergence test, okay, of the spring mass model. Okay, this okay, the convergence is of first order. Okay, so this is from the plot from here to here. Each time we double, okay, the grid size, okay, or okay, we shrink the grid size, okay, by half. Okay, and you see that they have a pretty good convergence here. However, numerically, okay, the convergence is only of first order. We haven't been able to achieve second order, okay, yet. Okay, and so that is what I just want to tell you. And this is early simulation, okay, and we compared with the experimental data by Xiaolin okay, of University Missouri. Okay, and that's very early study here. And after this simple model, we give a presentation at Columbia University, and one of the faculty members in the computer science department pointed out that the simple spring model, okay, is not a perfect model, okay, because it doesn't include, okay, what we call the tensor stimulus. It only have so we included, okay, the tensor we have that there is only a tensor stiffness, and we also need to include the angular stiffness. The angular if you only include the tensor stiffness, and you can still have a very good property of the Young's modulus, okay, but the tensor stiffness doesn't give you very good agreement in Poisson ratio. Okay, so we also included, okay, the angular stiffness, okay, by using Delancre's variation, okay, or Rayleigh-Ritz method, okay, to the spring mass model. It makes the model much more complicated, okay, and however, it gives you very good, okay, Young's modulus as well as Poisson ratio to represent, okay, the realistic, okay, fabric surface. And later we also found out that Poisson ratio, okay, is not very important in parachute simulation either. Now, why I say that? This is because, okay, when you have a parachute, the parachute canopy, okay, is it has the stress or strain, okay, uniformly in all directions, and therefore, okay, for most realistic simulation, we include, okay, Poisson the angular stiffness, but that relatively making the model more expensive and also the code more complicated. And sometimes we also just use the simple model. We try to compare the two results, okay, and of course, okay, when you measure the Poisson ratio, they don't agree very much. But when you talking about the parachute dynamics, it doesn't make very much difference. The second thing that we need to implement for the parachute simulation is the fluid, okay, canopy coupling. And we use the so-called impulse method. That is, okay, the mass point in the spring mass model or the fluid canopy receives, okay, 3 impulses. The first one, of course, is gravity. The second one is the fluid pressure from both sides of the canopy. And the third one is internal. The internal impulse is from its neighboring mass point. And there is a superposition principle that we can use to apply to each mass point. That's a nice thing about the spring mass model. And so we call this the impulsive. Actually, the impulsive method was given by Joe Myers. And he looked at it. He said, so you apply impulse to each of each component to the mass point and add it together. I said, yes, that's right. And the impulse of the fluid is a pressure difference on the 2 sides of the interface. Another thing that we need to take care of is a turbulence modeling of the parachute dynamics. The first paper we sent to Journal of Fluid Structure was returned because the editor said that parachute with canopy of like 10 meters, the Reynolds number is very large, and therefore, it is not physical, if you don't include a turbulence model. And so we also referenced other people's work, particularly Charlie Paskin, and they published. He and his student published 2 papers, one on 2-dimensional parachute simulation, and one on 3-dimensional simulation. He didn't use turbulence model, so I asked him, and he said, did you notice that our parachute is only a couple of centimeters in diameter? Oh, and then I realized, of course, if you have a parachute of that size, and you don't need to have turbulence model. And he said he did that because he wanted to avoid a turbulence model. So we included, and actually we tried several turbulence models. Actually, I think I should have these slides earlier. It's about the projection method. The fluid solver we use for parachute simulation is incompressible fluid solver. This is because the speed of the parachute compared to the sound speed of the air is much smaller, especially when you are in descent phase. It's just about a few meters per second, or at least about 20 or 10 meters per second. Now, in that regime, an incompressible solver is more efficient, and also easy to implement. So we use the projection method for the incompressible fluid solver. And many people who used the front tracking method before remember that we dealt with the problems like Rayleigh-Ritz instability using the compressible fluid solvers. That is because the fluid speed is relatively larger compared to sound speed, or the Mach number is much larger. And we tested several turbulence models. The current turbulence model is the K epsilon model here. It was implemented by one of my students, Gauguin, and he made several comparisons of different models. And what we found out is the following, that there is not much difference, okay, between different, okay, turbulence models, okay, and we ask why. The reason is that okay, the turbulence is in the weak floor, okay, of the parachute, while okay, the form pressure, okay, of the parachute, okay, is in this region where the fluid is relatively laminar. Okay, the turbulence is behind the canopy. And so that is our argument that the turbulence model is actually not participating, okay, or change the physics, okay, of the parachute simulation we had. However, okay, later we found out that okay, if we have a cargo or payload here, rigid body, which we'll talk about later, okay, there is a weak flow of the okay, cargo that will affect okay, the dynamics of the parachute. And so you can see from this picture that the turbulence floor is mostly behind the canopy. And we can also take a look at the streamline of the parachute. Another thing that we need to consider for the parachute simulation is porosity. Okay, the canopy is not impenetrable. Okay, and in fact, okay, the design of the parachute sometimes okay intentionally okay give the porosity of the parachute to stabilize okay the parachute dynamics. And so we use the parameter of gamma okay, to represent the porosity. Gamma equal to 0 means okay, no penetration. Okay, and gamma equal to 1 okay, means 4 penetration. So that for gamma equal to 1, it is equivalent to as if there is no canopy okay, as well. And we use the ghost fluid model. Okay, we use the ghost fluid method to model the pressure jump okay, across the interface and to consider the porosity. So I just show you some of the result of the okay, you know, this is the measurement, and we have here, and this is a simulation. This is a two-dimensional simulation. This is a okay non-penetrable okay fluid interface, and this is about half gamma equal to 0.5. So it's a highly porous okay fluid interface. You see that okay when gamma equal to 0, okay the velocity difference, okay, z velocity difference between here and here is very large, and this okay gives you a very unstable floor okay after the canopy. So this also tells you why okay sometimes parachute will intentionally give porosity of the canopy. And this is the okay vorticity. Okay, you can also see that the weak floor okay of this one become okay, unstable. Okay, this is a two-dimensional simulation. We also have three-dimensional simulation. Okay, and so this is benchmark test of the three-dimensional okay fabric interface, and we compared okay with experiment, and the model give a quite good agreement okay with experiment. And this is three-dimensional simulation with different porosity. Okay, and this is with gamma equal to, let me see, I don't have gamma here, but I remember that the gamma of this one is 0.1 and the gamma of this one is about 0.5. Okay, and with different porosity, you give a different cross-sectional area okay, of the parachute. Okay, and of course, okay, that will give you the variation okay, of the drag okay, of the interface. And so that is the floor okay, with low porosity and with high porosity. Okay, And in designing the parachute, it is a balance, okay, between, okay, the stability and the drag, okay, of the parachute. Another important topic, okay, of the parachute simulation is that you also have to couple. So we are talking about the classical physics almost everywhere, okay, Newton's law, okay, and we also want to include, okay, but except that Newton's law appear, okay, in different places in different ways, okay. In fluid dynamics, the partial differential equation, okay, Navier-Stokes equation, okay, and in the canopy, it is also Newton physics, but okay, it is spring model. And in the rigid body, okay, it's relatively simpler. Okay, you have two motions, okay, the motion of the center of mass and also the rotation about the center of mass. Okay, so we use the Euler angle and the Euler's equation to model, okay, parachute payload. This is, okay, this is graduate student mechanics course. So, okay, I will not give you the details, okay, of all the equations. This was implemented by one of my students, okay, and he has already graduated. Okay, and it's a very solid, okay, piece of work here. Okay, and what is this one? This is just to tell you that our parachute simulation can simulate all different kind of scenarios. Okay, for example, the broken string. This is actually suggested by one of the colleagues, okay, from Army Research Office, okay, Case Berger, and he said, "Oh, it's not. It's from Air Force, okay, scientists. They want to see the if we have the capability, okay, of with broken strings." Okay, I said, well, that is not very difficult. Okay, and we just set at a time. Okay, and suddenly let the string, okay, to be broken. Okay, and this is a in drop when, you know, for example, there is a shell, okay, and cut, okay, the interface. What is cut the string? Okay, what is going to happen? Okay, in the parachute. Okay, this is another scenario that what happens if you have, okay, uneven, okay, string. Okay, it sometimes happens. Okay, and how that is going to affect the dynamics of the parachute. And one of the important topic, okay, in parachute simulation is how to handle, okay, the collisions of different objects. We have, okay, the collision of fabric surface, okay, and we have collision between string cord, okay, and the fabric surface. We also have collision between fabric surface and rigid body, or between string and the rigid body. And this work was implemented by, okay, another student who has graduated, okay, and he used the AABB tree algorithm, okay. The basic, okay, idea, okay, is to detect, or the most challenging part is to detect the porosity, okay, of the parachute. We use the front tracking data structure, okay, and to do that. But one of my students also have the idea, okay, of, okay, modify this method. And currently this collision module is not parallelized. And so my student Brandon Balleton is trying to revise this method. So let me just first show you some of the, okay, benchmark, okay, simulations that we have, okay, on the existing code. Okay, this is the solid ball bouncing on the fabric surface. Okay, and this is the collision between the rigid body on the ground, and then the fabric surface to the ground. Okay, and this is the simulation of the, you can see also the fabric surface modeled as a spring model, and the colliding with a human body. Okay, and these are different collision scenarios. Okay, this is a fabric with a ball, fabric with a cube, and this is a string cord with fabric surface, and also this is multiple surface on the ball. Okay, and with all these collisions, we can simulate different not only the inflation and the terminal descending of the parachute, we can also simulate the landing. Now this is a landing without air, without fluid solver. Okay, it's just like in the vacuum. Okay, so you start with a flat one, it will remain to be, and it shows the collision between the rigid body to the ground, and also then the parachute canopy. And this one is with air, but it's also it's near the ground. Okay, and this is how parachute. The parallelization of the parachute coat is very challenging. Okay, the reason is that the time step for the spring mass model is very small compared to the fluid solver. So traditionally, fluid solver, we have used MPI to divide into subdomains to solve the PDE and then exchange data at the buffer zone. But this method fails when you use it to deal with the canopy. The canopy is a different monster, and its time scale is very different from the fluid solver. The time scale is very small. So the ideal way to solve the canopy or the spring mass model is to get them into one processor, and solve it. And then after solving it, you send it back to different processors for fluid solver. Fluid solver, we still use the domain decomposition method or the MPI. And however, when you collect all these mass point into one processor, you are making all other processors idle. And so how could you shorten the time needed to solve the canopy or the spring mass model? And it is at this point we sort of using GPU. And some of you may have used the GPU, and if you have kids play video games at home, you know that a lot of very quick motions in video game was computed by GPU. In fact, the GPU was first used by computer graphics people. And the spring mass model, it requires a lot of computation, but it doesn't require a lot of data transfer. And therefore, we can put this into GPU unit, and then let the vector solvers to solve it very quickly and then come back. So we use the hybrid parallelization, MPI, or domain decomposition as well, as the GPU. So the idea is the following, for each time step, you collect the pieces of the canopy from every processor into the master processor. And the master processor is going to send the connect the spring mass solver, okay, to the GPU. So GPU will get a very quick vectorized, okay, computation. And after that, you cut them into pieces and you send to, okay, different subdomains to couple with the fluid solver. So that's the idea, and we call it the hybrid, okay, parallelization. And we have some benchmark comparison, okay, about that, okay, and with GPU, okay, the time step for the canopy is much more shortened. So this is the result, okay, of different parachute models, okay, using GPU. And so this is the demonstration of 16 processes, 16, okay, subdomains for fluid, okay, and then the canopy come to one master, okay, processor and using GPU to solve it. So this is a hybrid simulation with 16, okay, processes, okay, of simulating, okay, this parachute simulation, okay, with a cubic and cargo, and this is with a, okay, sphere as a cargo, and this is with a human, okay, as a payload. Box, ball, and human. Well, I don't know. Let me see how much time I have here. Okay, so I think I'm going to just briefly also introduce you about the one of my other student, okay, Tembo, okay, and his work on the so-called preparation, okay, process of the parachute, that is folding. Okay, folding has a lot of interesting mathematics, okay, as well. We just realized when we did it. Okay, and so there is a so-called crease pattern. Okay, and the folding itself can be programmed. Okay, and the crease pattern can be foldable or not foldable. Okay, and there are necessary conditions for that. Okay, there are reference papers as well. Okay, most of this work, okay, are based on several other people's work. Okay, and I just give you some of the, okay, benchmark demonstrations. This is a folding of the corner box. Okay, and this is folding a corner, and this is a parachute folding. Okay, now when you fold it into this way, you will not be able to make it open, okay, because the fluid solver cannot penetrate, okay, this folded state. So what do? You let this state to relax, to have the spring mass model relax, just like you fold it, okay, and then you let it relax a while, and then there are gaps, okay, inside the fabric, and then you put into the fluid solver, okay, it will open. Okay, so this is called the spring mass relaxation process. Okay, so what I would like to say is that okay, the numerical simulation of parachute is a very interesting problem, although it is also a very complicated problem. There are a lot of things you have to deal with, okay, little by little, piece by piece. Okay, and we use the front tracking data structure. Some of you have been familiar with the front tracking, especially Xingfeng, okay, and you are familiar with front tracking, but you probably never realized that this, okay, method can also be used, okay, to study parachute, okay, inflation, and we did it. So I give you the general structure, okay, picture about how the front tracking method is used for the numerical simulation of the parachute inflation. And we still have a research front, okay, and one of my students, Brandon Belleton, and he is also in the audience, and his PhD thesis is try to, okay, progress, okay, our parachute model, okay, to couple with the compressible fluid solver. The incompressible solver is a good approximation when, okay, the relative speed of the parachute is less than 0.3 of Mach number. Okay, but there are high-speed parachute, okay, as well, and especially when the airplane, okay, first dropped, okay, people or dropped the cargo, okay, the time when the parachute just exit the airplane, the relative airflow is pretty high, okay, can be higher than 0.3 Mach. Another thing that we considered is that maybe, you know, our parachute model can be used to study, okay, the re-entry parachute, okay, as well. In fact, we sent a proposal to NASA, but it was not funded, okay. However, okay, we think that the study of the, okay, parachute model coupling with the compressor fluid is a very interesting problem. Okay, and it's also a good topic for a graduate student, PhD thesis. Okay, so Brandon, okay, was interested in this problem. And it is needed when Mach number is greater than 0.3, okay? Compressible fluid solver is less efficient because, okay, the CFL condition is restricted by the sound speed, okay? And generally speaking, is about 5 or 6 times more CPU times required for the fluid solver. Okay. However, also the compressible fluid turbulence model is more complex. Okay. One thing good about the compressible fluid solver is that it is relatively easier to parallelize. Okay, because all compressible fluid solver we use, okay, explicit method. Okay, the projection method for the incompressible fluid solver is always, okay, contains implicit steps. And for incompressible fluid solver, okay, you transform everything. Okay, there are 2 steps requires, okay, implicit solver. The first is the diffusion, okay, or Navier-Stokes diffusion process. The second is the projection, okay, process, which is the Poisson's equation. And you make them into matrix, okay, and you use hyper solver. Hyper solver is not developed by us, okay, so we depend on their, okay, parallelization, and if they cannot, okay, increase the efficiency, we cannot either, okay. But okay, for compressible fluid solver, okay, it is explicit, therefore we have a full control, okay, of the parallelization. Also, we know, okay, how to parallelize, okay, on compressible fluid solver very well. And Brandon has just started this work, so I just show you one, okay, animation he made, okay, on the high speed, okay, parachute simulation, and this is, okay, with a floor speed of 2.4 Mach number, okay, and so you see the shock wave, okay, shock front, bull shock, okay, near the payload, okay. So that is the general picture that I want to present, okay, about the parachute project using, okay, front tracking method. And we have a few publications, okay, I want to mention here, okay. And so let me try to briefly introduce what does these publications for. This is the first publication we had, okay. One of my students, John Dong King, he is now at Texas Austin. I mean, not Texas A&M, okay, as a faculty member there, okay. And this is the one we published in Communication in Computational Physics, okay, with Yinan Chen. I visited Taiwan that year, okay, in my during my sabbatical, and so we worked to collaborate together, okay, and published this paper, okay. And this is a paper, okay, on the validation of the spring mass model. Okay, and I visited Edwards Air Force Base, okay, and their scientist, okay, Daniel Rizzo, okay, you know, the joint, okay, we collaborated, okay, on this work, and also Richard Charles, okay, of the Army research lab. And these are just, this is a paper about the porosity study, okay, and it was published in AIAA. And these are the references of other people, okay, and this work has been generously supported by the Army Research Office. And in particular, I'm very grateful to Joe Myers, and he is very supportive to our research work. Okay, just to show you the capability of our code, and this is another interesting, when we have the code here, and students sometimes just like to play it. Okay, so this is one of their play of the airbag simulation. Okay, and they play also, we have the rigid body simulation with, so we can simulate bullet. And actually I can compare with the real picture of the bullet. It's very similar to that. Okay, and this is a three-dimensional bullet simulation, and this is a grenade simulation. Okay, sometimes we just play it for fun. Okay, and this is how we can use front tracking method to phase transit. I don't have time to talk about this. Okay, this is another thesis by a student, and using this problem, we made a conservative front tracking. This for the precipitation or the crystallization problem, we can have fully completed 100% conservative front tracking code. Okay, so that is my talk. Okay.
Thank you.
Thank you.
So any questions?
Hey, Xiaolin, let me ask you, how about the deployment phase? Can your code simulate that?
How well? I really have to. I once was thinking of there are parachute jump places in Long Island. Okay, I'm just a little bit scared. Okay, I'm too old to do that. Okay, well, as I mentioned to you that we can probably simulate quite a lot of scenarios. Okay, like broken strings, and uneven strings, and you just have to tell us exactly what you want. Okay, and we can try to implement. Now, I'm not going to say that we can do everything. Okay, for deployment, what is deployment? What is involved in the deployment? I mean, what we are trying to do is that we're trying to simulate the parachute from the half open state to a fully inflated state. Now I can only see this at least half open because it's completely fully, the fluid solver can never penetrate into the gap of the fabric. And therefore, you don't have physics of the fluid there.
Mm-hmm. Well, and also in the porosity modeling, you have 3 different ways to model that. You chose one, but I wonder the other 2, I guess they have a slightly different physics, right? Are they giving you the same consequence?
You mean porosity?
Yeah, porosity.
We use the ghost fluid method.
Yeah, but you have 3, you mentioned 3 different ways to do that.
I mentioned 3 different penetration ratio.
Right.
Okay, this is gamma equal to 0, gamma equal to 2.5. I didn't mention 3 different models.
No. If you go a little bit further, I think you mentioned 3 different ways to model that.
Oh, that's a turbulence model.
I thought it's a porosity.
No, porosity, we only used one model, the ghost fluid model.
Okay.
To do that.
Okay.
Any other questions? Okay, no more. Let's thank Professor Xiaolin for his nice talk.
Thank you very much. Okay, nice to
Very impressive.
meet all your people.
Yeah.
Very impressive. Maybe you should really simulate some, real world event.
Okay, well, it's a lot of fun also.
Yeah. Yeah.